Okay, so we've solved the fundamental problem that the sun posed. We now know what the sun's source of energy is. Now we trust our models and we try to use this understanding to figure out what we can about how the sun is constructed, what its structure is. How do we study the structure of the sun? Well, lots of numerical modeling. We measure reaction rates and properties of hydrogen here on Earth, and then try to apply them, but it's hard to simulate the conditions of the sun here on Earth. Another important measurement tool is helioseismology, just as we infer the interior structure of the Earth from the propagation of sound waves through the Earth. Sound waves propagate through the very compressed hydrogen that is the sun, and the properties of that propagation can be used to infer interior properties of the sun. How do we generate sunquakes? Well, we don't need to. The sun oscillates. The sun is a fluid system, it oscillates, and what we do is we measure the Doppler shift of radiation from spectral lines, actually, from particular points on the sun, and we notice that when we plot this, that the sun is wobbling in particular ways, and studying the frequency and spatial structure of these wobbles, these resonances. The sun is basically ringing like a bell, and you can try to hear the shape of a bell, and that's what we're trying to do, and that's one of the main tools we have for verifying our modeling predictions for the structure of the interior of the sun. And so this is this plus modeling is how we understand everything that happens between the core, that inner densest part and hottest part where fusion is ongoing, and the photosphere, which is the name we give the outside of the sun, the part that we see. So the part that we see is the photosphere. It makes the photons. And now, we have our understanding of a spherical object. It's a fluid object. It's held together by gravity, and it's held up against gravity by the intense heat and pressure and radiation pressure generated by all that energy being released in the interior, in the core. And like with any object in equilibrium, density and pressure and likewise temperature increase as you move from the surface of the sun in. The core is the hottest and densest, and as you move out, the sun is cooler and less dense, as one expects for hydrostatic equilibrium. This is what holds the sun up against collapse due to gravity, is the heat coming in from the core, and here is what we understand in terms of the structure of the sun. So the internal core of the sun occupies the regions to within a quarter of the solar radius. The solar radius is the radius of the photosphere by convention, and that's about 696,000 kilometers. And from the center, about a quarter of a solar radius out, that is the core, that is the region where 99% of the fusion power is generated. Temperatures at the center of the core reach about 15 million or 16 million Kelvin, and at the outside of the core there's 7 million, and by that time fusion is becoming completely inefficient. The density too decreases. At the center of the sun, the density of hydrogen is 150 times the density of water, and by the time you get to the outside of the core, it's only 20 times the density of water. And this region, the inner quarter solar radius of the sun, contains 40% of the mass of the sun. This might not sound impressive until you remember that volume scales like radius cubed. So we're talking about a 64th of the volume of the sun, containing almost half the mass. This is indeed far denser than the rest of the sun. This is the region where hydrogen is most extremely compressed. And importantly, the core is in a state of equilibrium in the following sense. If fusion rates in the core decrease, for example, then the core is producing less energy. There is less radiation pressure and less thermal pressure. The core cools a little. What this does is that then the force of gravity, the weight of the outer layers of the sun, compresses the cores a little bit. And when the core compresses, densities and temperatures increase. Densities because it's compressing, temperatures because it's now heated by Kelvin-Helmholtz heat. It's contracting. This, in turn, increasing the temperature and the density, increases the rate of fusion. So there's this self-regulating thing. If, on the other hand, the rate of fusion were to increase, the core would heat up, expand a little, the expansion would cool it down, and this would decrease the rate of fusion. So the rate of fusion is, in fact, controlled by the weight of the outer atmosphere of the sun. In other words, the luminosity is determined by the mass of the outer layers of the sun pushing down on the core, determining how much of the sun is going to be compressed. When we talk about other stars, this is going to be very important. the luminosity of a star is determined essentially by its total mass. That determines how much of the hydrogen is compressed enough in the core and hot enough to undergo fusion. This is the internal, this is sort of the engine of the sun. This is where the energy gets produced. And then there is what you might call the analog of the mantle of the sun, the next layer, labeled number 2 here. It's called the radiation zone. It extends from a quarter of the solar radius out up to about 0.7. Temperatures in the radiation zone decrease from the 7 million at the outer boundary of the core to only 2 million Kelvin at the outside of the radiation zone. Densities too decrease down by the outside of the convection zone. The sun has thinned out to merely the density of water. It's merely, but remember this is hydrogen gas at that density. Throughout this region, temperatures are in the millions of Kelvin. There are no atoms here. The interior of the sun is a plasma. In other words, nuclei, mostly hydrogen nuclei, and electrons move completely independent of each other. There is no coherent atomic structure that survives at these temperatures. The thermal energies of things are much higher than the binding energies of atoms. And this region is characterized by the fact that the way energy is transferred, so of course there's a net transfer, energy is produced in the core, and it flows out and then is radiated out to heat us. And the mode of heat transfer in this part of the sun is radiation. Now, this does not mean that this part of the sun is transparent. It's radiation diffusion. In other words, high-energy photons produced, gamma rays, produced in the core, are emitted. They're immediately absorbed by interaction with the charged particles in the plasma, and then re-emitted and reabsorbed and re-emitted and reabsorbed. An average photon, or the energy of an average photon, takes 170,000 years to travel the distance from the core to the outer edge of the radiation zone. So this is not moving at the speed of light. This is some very slow diffusion. When you have charged particles in a plasma, then there's a strong interaction between the charges and the radiation, and radiation does not penetrate a plasma the way it penetrates a neutral gas like the light in this room. But the mode of energy transfer is radiation diffusion, and that means that energy moves up, but the plasma itself is not in any undergoing any macroscopic global motion. This changes in the outer mantle of the sun. That's the convection zone between 0.7 of the solar radius all the way out to the photosphere. And here temperatures decrease very rapidly from 2 million degrees in the interior down to the surface temperature of the sun that we measure, 5,777 Kelvin. Densities decrease from about the density of water to essentially zero. And the mode of heat transfer in this region is convection. In other words, in this region, the plasma becomes opaque, essentially, and the most efficient mode of heat transfer becomes hydrogen that is heated at the inner bottom of the convection zone by the incoming radiation from the radiation zone, rises and then cools when it reaches the surface, and then sinks again, so you get these convection cells. This is responsible for the sort of granular appearance of the photosphere, which is very evident in the following movie. Here we see a very high-resolution image of the solar surface. Details as small as 500 kilometers across can be measured, and for proportion, we've indicated here the size of the Earth, so that you know the size of the object we're looking at. We're looking near a sunspot, and you see the sort of granular shape of the surface of the sun. This characterizes the way the photosphere looks. In the center of a granule, you imagine, is where warm gas is welling up, and then in the edges, between the granules, is where cooler hydrogen is seeping back down, and because it's cooler, we observe a lower temperature. T to the fourth from Stefan Boltzmann means those regions radiate less, which is why they look dark. They are still very warm and they are radiating, but they are radiating less than the surroundings. And it's interesting to watch the dynamics of this process. We see sort of constantly changing convection patterns. There's not a stable convection pattern on the sun, but there's these oozing, changing patterns. So we've gotten all the way out to the outside of the sun, but of course, like the Earth, the sun extends beyond its surface. There is more of the sun outside the photosphere. the sun, that we might call that the sun's atmosphere. There are several layers. The density of gas decreases dramatically, but it turns out that, so there's not much there in the solar atmosphere. The mass of the sun is below the photosphere, but the temperature, it turns out, because of various processes, some of which we'll discuss, in fact increases with altitude. The first lower layer of the atmosphere is called the chromosphere. That's the layer up to an altitude of 2,000 kilometers above the photosphere. And in the chromosphere, the temperature rises to about 50,000 Kelvin, but the density decreases by 7 orders of magnitude. So there's not much gas there. It's very hot. But we don't see the chromosphere. We're blinded by the photosphere, even though the chromosphere is hotter, because the T to the fourth is outweighed by the fact that there's basically nothing there compared to that. To observe the chromosphere, we use the fact that in the chromosphere there are hydrogen atoms. Hydrogen atoms emit characteristic frequency spectral line at 656.28 nanometers. It's the H-alpha line. We've talked about it before and will again. And so when you take pictures of the sun using the filter that allows only that wavelength through, you're essentially taking a picture of the photosphere, and this movie is indeed such a picture. Those dark finger-like shapes are called spicules. They reach thousands of kilometers up out of the atmosphere of the sun, and their precise dynamics and structure are not well understood. But again, we get this image of the roiling atmosphere of the sun, and we'll see more of that. Above the chromosphere, the temperature jumps very rapidly as you enter the corona, and the temperature jumps from the 50,000 at the top of the chromosphere to 2 million Kelvin. This is not a fusion-going region. The density is down to 10 to the minus 12. There is, again, virtually nothing there. And this region extends, as you can see in this beautiful coronagraph, out to 1 or 2 solar radii. So the blocked out region, a coronagraph, is a telescope that blocks out the blinding illumination of the photosphere so that you can see the rest. Another way to see the corona is wait for the moon to play the role of a coronagraph and block out the central disk of the sun. And during a total eclipse, indeed, people take beautiful pictures of the corona. You can find many of them online. We see here a few spicules. These red-ish protuberances are spicules in the chromosphere. I told you that the dynamics is not understood, but the red color is the reason that part of the atmosphere is called the chromosphere. Because of the high temperatures, we observe the corona ideally in ultraviolet or X-ray wavelengths, where it competes with the sun and where it emits most of its light. The fact that the temperatures are millions of Kelvin allows many of the particles, as we did in our little helium calculation for Earth, the fastest particles in the corona, where they're all ionized because the temperature is millions of degrees, can in fact achieve escape velocity and stream away from the sun. And what we call this stream of charged particles, which achieve escape velocity and move away from the sun, is the solar wind. We've talked about its effects. This is where it actually comes from. And the solar corona, as we can see in this movie, is an active and interesting place. The white disk here is the photosphere. The coronagraph blocks more of that. We see coronal mass ejections and flares bursting out from the sun. We'll talk about the mechanism. And we interestingly see the detector being attacked by streams of these charged particles. That's that sort of staticky stuff. Those are the streams of charged particles hitting the detector. And this is an image from 2001. And I believe that if we wait long enough, or if you watch that image to the end, you will actually see something transit behind the sun. But you can look at that at your own leisure later.